Dear students, let us continue the third unit of chemistry, the classification of elements and periodicity in properties. In today's session, we will start with a very important concept, electron gain enthalpy. Electron gain enthalpy. How you define this? See, electron gain enthalpy is defined as change in enthalpy that occurs when an electron is added to an isolated gaseous neutral atom. Let me repeat this. Electron gain enthalpy is the change in enthalpy that occurs when an electron is added to an isolated gaseous neutral atom. See here, it is an electron gain. An atom gains an electron in this process. Consider a gaseous atom, X gaseous. If you add an electron plus E minus, you get a gaseous neutral, you get X minus gaseous. A negative ion is formed. Now, enthalpy change takes place in this process. Change in enthalpy delta H, Eg, Eg stands for electron gain, delta H change in enthalpy. Now, delta H may be positive or it may be negative quantity. That means delta H may be positive, means the process may be endothermic, okay, or negative, delta H negative means heat released in the process or the process is exothermic. So, in this process delta H can be positive or it can be negative based on the nature of the atom, based on the nature of the atom to which you have added the electron. See, if you see the periodic table, group 17 elements have very high negative electron gain enthalpy. In the periodic table, so you can see the group 17 elements which are having very high negative electron gain enthalpy. Why it happens? See, the electronic configuration of group 17 elements is NS2 NP5. NS2 NP5. If they gain one electron, the configuration will be NS2 NP6, that is the configuration of the next higher inert gas. For example, if fluorine gets an electron, it attains the configuration of neon, a stable configuration. You know, the inert gases are having stable electronic configuration, we call them as octet configuration. Therefore, these elements, the elements of the group 17, they always tries to have the electron to attain the stability. Therefore, they are looking for the electron, always they are looking for the electron. So, whenever they get the chance to take the electron, they readily accept the electrons. Therefore, these elements are having great affinity for the electrons. So, they release the energy. When they get the electron, they release the energy. So, this is about the group 17 elements. Then group 18 elements. Group 18 elements, they all these are having positive electron gain enthalpy. Positive electron gain enthalpy. So, positive electron gain enthalpy, why? Inert gases have NS2 NP6 configuration except helium. It has only NS2 configuration, 2s2 configuration, right? Already they have a stable electronic configuration. If they gain an electron, if they gain an electron, it leads to the formation of an unstable electronic configuration. They become unstable if they get an electron. That's the reason they're never ready to take the electron. They don't want to be unstable. That's the reason they have positive electron gain enthalpy. Positive electron gain enthalpy is there for group 18 elements. Now, the unit of electron gain enthalpy is kilojoules per mole. The unit of electron gain enthalpy is kilojoules per mole. Now, if you see the electron gain enthalpy, let us see the trends in the periodic table. Along the period, in general, electron gain enthalpy becomes more negative, isn't it? The electron gain enthalpy becomes more negative across the period. That means the energy released is more and more if you go like this. Now, why the electron gain enthalpy becomes more negative across the period? Across the period, the effective nuclear charge increases, thereby the atomic radius decreases. Atomic radius decreases. So, it is very easy to add an electron to the smaller atom. That is the reason these atoms, group 17 elements, if you move like this, the atomic radius decreases, and thereby the electron gain enthalpy becomes more negative. Down the group, what happens? The electron gain enthalpy becomes less negative. Down the group, electron gain enthalpy becomes less negative, because as you go down the group, atomic radius increases. See, if you go down the group like this, the atomic radius goes on increases. Say you have the positive charge here, you have the electron, there should be force of attraction. There is a force of attraction between the positive charge and the negatively charged electron. As the distance between the nuclear charge and the electron increases, the force of attraction on this decreases. Therefore, on moving down the group, the electron gain enthalpy becomes less negative. Then we will have to see some abnormalities. The very important point for the examination. Electron gain enthalpy of chlorine is more negative than that of fluorine. In general, what I said, on moving down the group, electron gain enthalpy becomes less negative, but electron gain enthalpy, you can see the abnormalities here. Electron gain enthalpy of chlorine is more than that of fluorine. Okay, and all these values, whatever we have given here, the values are in kilojoules per mole. Okay, the unit is kilojoules per mole for all these values. Why chlorine has higher negative electron gain enthalpy than fluorine? The one important question for the examination. See, in case of fluorine, you know the configuration 1s2, 2s2, 2p5. In case of chlorine, the outer electronic configuration is 3s2, 3p5. Okay, chlorine 3s2, 3p5. The added electron fluorine goes to n is equal to 2 level, second quantum level. In case of chlorine, it goes to n is equal to 3 level, that is goes to the third quantum level. Due to the smaller size in case of fluorine, the size of the atom is smaller. Therefore, the repulsion between the electrons, see already these electrons are there in the valence shell, they try to repel the incoming electron. So, there is a force of attraction between the nucleus and the incoming electron, and the repulsion between the electron already present in the atom and the incoming electron. So, the repulsion is greater due to the smaller size of the fluorine, electron repulsion is greater. Thereby, it has low electron gain, negative electron gain enthalpy. But in case of chlorine, the electron is added to in the bigger space, or n is equal to 3 means size of the chlorine is bigger. Therefore, electron repulsion is less. That is the reason this abnormalities are observed. Similarly, you can see the electron gain enthalpy of oxygen and fluorine. Same reason, oxygen enthalpy of sulfur is more than the electron gain enthalpy of sulfur is more negative than that of electron gain enthalpy of oxygen. Same reason, because here the electron is added to the smaller shell. So, the electron repulsion is greater in case of oxygen, and it is electron repulsion is less in case of sulfur. So, these are the abnormalities to be noted for the examination purpose. After this, let us move to another important concept. Electronegativity, this term is applicable only for the covalent compounds, not for the ionic compounds. Okay? Consider an HF molecule. You know, there is a covalent bond between hydrogen and fluorine. So, now an electron pair is shared between hydrogen and fluorine like this. Thereby, a bond is formed. The sharing is 50-50, hydrogen gives an electron, fluorine gives an electron. Equal sharing of contribution is equal, and an electron pair is shared between these two. Once the bond is formed, see, fluorine is greater electron withdrawing capacity. It has greater tendency to pull the electron share towards itself. So, this electron pair now is more towards the fluorine atom, and fluorine atom gets a fractional negative charge, hydrogen gets a fractional positive charge, and the polarity is produced. You get the two poles, one is negative pole and the positive pole. Now, the electron is shifted towards the more electronegative atom. But in case of electron gain enthalpy, see the difference. Electron gain enthalpy means we are adding an electron to an atom, or atom gains an electron. Electronegativity, shifting of the shared pair of electrons towards more electronegative atom. See, different scales are given to compare the electronegativity values for the elements. One is Mulliken scale, another is Pauling scales, other scales are also there. Let us see the Pauling scale. You have lithium, sodium, see, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. The electronegativity value, see, 4 4.0 is arbitrarily fixed to fluorine by Pauling. Now, it is a relative quantity. There is no unit for electronegativity values. Ionization enthalpy is measured in kilojoules per mole. Electron gain enthalpy is also measured in kilojoules per mole. Now, electronegativity do not have any units. So, the value of 4 is given to the fixed for the fluorine. Now, the value of oxygen is 3.5, value for nitrogen is 3.0, chlorine, carbon 2.5, for boron the value is 2.0, beryllium the value is 1.5, and for lithium the value is 1.0. If you go down, lithium, sodium, potassium, rubidium, cesium, and lithium value is 1.0, sodium is for the value is 0.9, potassium has got 0.8, rubidium 0.8, cesium the value is 0.7. Here group 17 elements: fluorine, chlorine, bromine, iodine, and astatine. Fluorine the value is 4.0, chlorine 3.0, bromine 2.8, iodine the value is 2.5, for astatine the value is 2.2. See the trends. Electronegativity increases across the period. The most electronegative element in the periodic table is fluorine. You always remember this. One important point to be noted for the examination purpose: name the most electronegative element in the periodic table. Which one? Fluorine is the most electronegative element in the periodic table. Now, across the period, in general, the electronegativity value increases. Electronegativity value increases across the period. Why it increases? You know this, across the period, effective nuclear charge increases, then the atomic radius again decreases, thereby the electronegativity increases. Electronegativity increases. On moving down the group, electronegativity decreases. Electronegativity decreases. This is again because of the increase in the atomic radius on moving down the group. So, that is about the electronegativity. See, what is electronegativity? It is the quantitative measure of the ability of an atom in a molecule to attract shared pair of electrons towards itself. Its trends along the period, electronegativity increases, down the group electronegativity decreases. Now, electronegativity and non-metallic properties. If you see the values, so these are the non-metals in the periodic table. Right side you have non-metals. As the electronegativity value increases, non-metallic property increases. As the electronegativity value decreases, the metallic property increases. Metallic property increases. So, with this, this electronegativity complete. Now, we will see the highlights of this topic. Let me go for the highlights of this topic. Main point, what are the main points to be discussed to be remembered by keeping examination in mind. First one is modern periodic law. Modern periodic law. What the law states? Properties of the elements are the periodic functions of their atomic number. One important point for the examination. Second point to be remembered is general electronic configuration. Electronic configuration of S block, P block, D block and F block elements. Remember, the general electronic configuration, general valential electronic configuration or general outer electronic configuration. For S block you have NS1 to 2 configuration, alkali and alkaline earth metals. First group elements have NS1, second group they have NS2 configuration. In general, the S block elements have NS1 to 2 electronic configuration. For P block, the general electronic configuration is NS2, NP 1 to 6. NS2, NP 1 to 6 for the P block elements. Now for the D block elements, N-1 D 1 to 10, NS 0 to 2. This is the configuration for D block elements, valential electronic configuration for D block elements. Now for F block elements, N-2 F 1 to 14, N-1 D 0 to 1 and NS2. We can expect one question on this for the examination. General electronic configuration of S, P, D and F block elements. Next we discussed about the atomic radius. What is atomic radius? Atomic radius is the distance between the nucleus of an atom and the outermost shell of electrons. Normally it is measured in picometer, right? So distance between the center of the nucleus and the outermost shell, that is atomic radius. Atomic radius. Its strands to be remembered. Along the period, what happens to the atomic radius? Atomic radius decreases. Down the group, what is the trend? The atomic radius increases because new shells are added here. Along the period, what happens? Along the period, effective nuclear charge increases, thereby the electrons are held tightly by the nucleus, so the atomic radius decreases and the electrons are added into the same principal shell. After this we discussed about the covalent radius, ionic radius. Okay, ionic radius. What do you mean by ionic radius? It is the distance from the center of the nucleus to the point up to which the nuclear charge has the influence on its electron cloud. Distance from the center of the nucleus and the point up to which the nuclear charge has the influence on its electron cloud, that is ionic radius. Now isoelectronic species. Isoelectronic species, we discussed a little bit about isoelectronic species. Iso is same number of electrons. Species, maybe atoms or ions containing same number of electrons, they are called as isoelectronic species. NLA atoms or ions containing same number of electrons, they are called as isoelectronic species. In case of isoelectronic species, what happens to the atomic radius? Sorry, what happens to the radius of the species? Not the atomic, need not be atomic radius, it may be ionic also. See, the isoelectronic species example, we have N minus 3, O minus 2, F minus, then Na plus, all these are isoelectronic species, Mg2 plus, Al3 plus, okay. See the atomic radius, all these are having same number of electrons. So, atomic radius is in the order, N minus 3 has highest radius, the radius is in this order, this has the smallest radius, and the radius this decreases in this order, because this has the higher effective nuclear charge. Effective nuclear charge comes from the positive charge present in the nucleus. The positive charge is due to the protons present in the nucleus. It has, see, atomic number is 12, more number, 12 number of protons. So, it can withdraw the 10 electrons, it can hold the 10 electrons very tightly. Whereas in case of N minus 3, the number of electrons are 7 and number of protons are 7 and number of electrons are 10. So, 7 protons has to attract the 10 electrons. Here the 12 protons has to attract 10 electrons. So, naturally the force of attraction on the electron is more here. As they attract more tightly, the radius decreases. So, that is about the isoelectronic species. Then the radius of the cation and the radius of anion. Cation and its neutral atom. For example, Na and Na plus. Na and Na plus plus electron, right. Cation is formed by losing an electron. Then what happens? Here in case of sodium, you have 11 electrons and 11 protons. In case of sodium, you have 10 electrons and 11 protons. So, therefore, the force of attraction on the electron is more here. These nuclear charge can hold the electron more tightly. That is the reason Na plus has smaller size and compared to the size of its neutral atom. Always you take any atoms, the radius of the cation is smaller than its neutral atom. So, because by losing an electron, what happens? Number of effective nuclear charge remains same, number of electrons decreases, thereby the radius decreases. In case of negative ion, look here, for example, Cl plus electron, it gives Cl minus. So, this is the neutral atom, this is the negative ion. Anion, this is called as anion. Anion is formed by gaining an electron. Then what happens? Effective nuclear charge is same here and here, but number of electrons is more in this species. Therefore, anion has greater size or the larger size compared to the radius of its neutral atom. This point has to be remembered. Radius of the cation and its neutral atom, radius of anion and its neutral atom. Now, next concept we discussed is ionization enthalpy. Ionization enthalpy. So, the ionization enthalpy, amount of energy required to remove an electron from an isolated gaseous neutral atom, that is called as ionization enthalpy. Amount of energy required to remove an electron from an isolated gaseous neutral atom. X gaseous atom, it gives X gaseous plus electron. This is how we explain the process. And remember, always delta Hi, ionization enthalpy, it's always a positive quantity for ionization enthalpy. The reason is, to remove an electron, energy has to be supplied to the atom. Otherwise, you cannot remove the electron. So, therefore, this process is always endothermic process. Endothermic process, we are removing an electron. If you remove the first electron, it is called as first ionization enthalpy. Energy required to remove the first electron. From where you remove? The electron is removed from the valence shell, outermost shell. Later, if you remove one more electron from this, X plus gaseous, it gives X 2 plus gaseous plus electron, and second ionization enthalpy will be more than the first ionization enthalpy, higher than the first ionization enthalpy. Now, whatever the energy required here in this step, that is called as second ionization enthalpy. Second ionization enthalpy. Now, it's trends. So, along the period, ionization enthalpy increases. Down the group, ionization enthalpy decreases. Down the group, ionization enthalpy decreases. Again, the same reason. So, main concept what we are deciding factor here is atomic radius. Atomic radius is the main factor which decides ionization enthalpy, electron gain enthalpy, electronegativity for all. So, again, across the period, ionization enthalpy increases, down the group ionization enthalpy decreases. But in between you have to observe some abnormalities. Where the abnormalities are there? So, second group elements you have beryllium and boron. This side you have nitrogen and oxygen. In general, what I said, if you go like this across the period, the ionization enthalpy increases, but ionization enthalpy of beryllium is more than that of the boron. Ionization enthalpy of nitrogen is more than that of oxygen. Why? Important for the examination. This type of the abnormalities you have to observe, and you have to remember the reason behind this. Why? Here you are removing the s electron, which is more nearer to the nucleus. So, beryllium you have the configuration 2s2, 1s2, 2s2. Here 1s2, 2s2, 2p1. So, removal of the p electron is very easy compared to the removal of s electron. Therefore, this has higher ionization enthalpy, and boron has comparatively lower ionization enthalpy. In case of nitrogen and oxygen, again same thing. Nitrogen has stable half-filled configuration. Therefore, nitrogen has higher ionization enthalpy. Later we discussed about today's concept, electron gain enthalpy, and then electronegativity. You remember the trend is same except for atomic radius. For ionization enthalpy across the period decreases, across the period ionization enthalpy increases, electronegativity increases, electron gain enthalpy becomes more negative. Down the group, your atomic radius increases, then ionization enthalpy decreases, electronegativity decreases, then electron gain enthalpy becomes less negative. So, I hope you understood this chapter, and dear students, My humble request is work hard, learn to sacrifice, learn to struggle. Hard work is the only key to open your dreams. Okay, thank you. All the best.